Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 6, Lesson 2, Radical Expressions. After today's lesson, you'll be able to write an equivalent radical expression. In other words, you are simplifying radicals. We're going to learn some new rules, some new properties, the product property of cube roots and the product property of square roots. For the critique and explain, we have this table showing the relationship between the area of a square and the side length of a square and the square root of the area. Okay, a square with an area of 4 and a side length of 2 is shown on the right. So it makes sense. If the side length is 2, then the total area is going to be 4, right? And the side length is just represented as the square root of the area. So if you remember the formula for area of a square is side squared. If I want to solve for s, I take the square root of both sides. So this side length would equal the area or the square root of the area. That's all it's showing. So what is the side length of a square with an area of 49? Well, to find the side length, I just take the square root of the area. So the square root of 49 is 7. Part B, between what two consecutive integers is the square root of 20? So think back to middle school, maybe even 6th grade. We're thinking of perfect squares that the integer 20 falls in between. So 20, think of our perfect squares. We've got 4, 9, 16, 25. Okay, so the number 20 is in between 16 and 25. If I take the square root of all of those, because I'm looking for the square root of 20, what's the square root of 16? 4. What's the square root of 25? 5. So that means the square root of 20 is going to be somewhere in between the integers 4 and 5. You could even say it's going to be closer to 4 since 20 is closer to 16 than it is to 25. Part C, think of 3 squares that have a side length between 3 and 4. What is the area of each square? Well, just pick some numbers, some rational numbers, like 3.25. If the side length is 3.25, then you're going to square it. What would the area be? 10.5625. If the side length was 3.6, that's a number in between 3 and 4. If you square that to find the area, you'd get 12.96. Let's do really close. Not quite 4, 3.99. If I square the side length, I'll get the area. So the area then would be 15.9201. You could pick any number in between 3 and 4, any decimal you wanted, and just square it to find the area. Example 1, writing equivalent radical expressions. So this is the product property of radicals. If you have a number, you can break it into factors inside the radical, and then we can simplify that. Okay, so that's what this rule is. You can simplify it into factors, and then each factor gets its own radical. You can split the radical and then simplify. Okay, so let's take a look. We have the square root of 63. What are factors of 63? When you're thinking of factors, you want to be focusing on getting at least one of the factors to be a perfect square. So, does 63 have a perfect square factor? It sure does, because one of the factors is 9, which is a perfect square. I don't think you really need to do all this part. Okay, so then you can write it as 9 times 7, and then split the radical. Each factor gets its own separate radical, and then you simplify. What is the square root of 9? It is 3. 3 times the square root of 7. Just remember, these are products, so we're multiplying everything. Okay, so look for perfect square factors, and then split the radical and simplify. Part B. Now we're going to, again, look for perfect squares. Okay, so we have to think a little bit more strategically. Are there perfect squares in each of these factors? They're already divided for us. We can't multiply them together. They don't have the same base. We can't do any exponent rules. So let's just look at 2 to the 7th. Is there a perfect square in there? So let's think, what does this mean? 2 to the 7th is 2 times 2 times 2 times 2 times 2 times 2 times 2. Okay. What if I did, grouped it into 3s? Well, there's 2 to the 3rd squared, right? So there's a perfect square right there. So I can rewrite it as 2 to the 6th times 2. Okay, 2 to the 6th times 2 would be the same as 2 to the 7th, because here's that extra 2. And I know 2 to the 6th I can simplify to be 2 to the 3rd. I don't think you need to do that part. This step is kind of confusing. So 2 to the 6th, if I take the square root, I get 2 to the 3rd. Okay, 5 squared, well, that's 25. What's the square root of 25? It's 5. And then I'm still left with the square root of 2. So then we're going to multiply. What's 2 to the 3rd? Well, that's 8. 8 times 5 is 40. And then we're going to write 2 to the 1/2 as the square root of 2. So then 40 times the square root of 2. I don't think you need to. I think it's easier if you don't convert them to rational exponents. Honestly, that might confuse you a little bit. So I wouldn't do this part. I would just leave it as the square root of 2. Try it number 1. Let's rewrite these. We're going to simplify the radical. So again, we're looking for perfect square factors. What are factors of 44? 4 times 11. Is one of those a perfect square? Yes, 4 is a perfect square. So then we're going to split the radical. Each factor gets its own little radical. We're still multiplying them. Okay. What's the square root of 4? 2 times the square root of 11. And then when we put them back together, we can simplify it and not write the dot. Letter B, we have 3 times, I'm going to separate that, times the square root of 27. What are factors of 27? 9 times 3. Is one of those a perfect square? Yes, 9 is a perfect square. That's what I want. Split the radical. So this equals 3 times the square root of 9 times the square root of 3. I separated it for a reason. What's the square root of 9? 3. And now we can simplify. What's 3 times 3? 9 times the square root of 3. Example 2. How can we write an expression for the product of these two radicals? So now, if we are multiplying radicals and it's the same root, we can just put it all under one big square root. So that's what we're doing. So we can multiply the constants. 3 times 2 is 6. And then everything else gets under the radical. We're just multiplying 5x times 15x cubed. So that's what we get here. Now we're going to break apart these and look for prime factors. And we're still looking for perfect squares. So we can separate 15 into 3 times 5. And I like that. Why do I like that? Because then I can group the 5s together. And I have a square, perfect square. The square root of 25 is 5. Okay, so I like that. The square root of x to the 4th is just x squared. Okay. And then that leaves, so I'm going to show you. I'm going to cross out what we did. We did the square root of 25, and we did the square root of x to the 4th. So again, if maybe it helps if you write it out. X to the 4th equals x times x times x times x. I can group them into two squares, x squared times x squared. And when I take the square root, then I'm just left with 1, x squared. And so then what's left is the square root of 3. So then we're going to multiply everything. 6 times 5 is 30 times x squared times the square root of 3. So again, when you're multiplying, when you have products with the same root, you can combine them all under one radical. Then you're going to break each factor or each piece into prime factors and see if you can combine them in some way to get perfect squares. Try it number 2, writing an expression for each product without perfect squares in the radicand. So we want to get the perfect squares out from underneath the square root so that they're simplified. Okay, so let's first look at multiplying my constants. Okay, so 1/2 times 4 is 2, and then everything else is going to be under one radical. I have 21 times x to the 3rd times 7 times x squared. Let's break apart our factors a little bit more. Can I separate 21 into factors? Yes. This is going to be helpful. I'm going to have 7 times 3. And then x to the 3rd and x squared. I'm going to put those at the end. This is x to the 5th, right, if I add the exponents. Okay, look here. I have 7 times 7, which is 49. I'm going to separate them all now too. Square root of 3. Okay, so do you see what I have? I did this. I just combined them. And then the square root of 3 has its own radical. Okay, let's deal with x to the 5th. X to the 5th, I can think of a perfect square in there. X to the 4th times x. Okay, so I'm just going to rewrite it like that. Times x to the 4th times the square root of x. So that's what I got here. Remember, they each get their own radical. Now I can simplify. So what's the square root of 49? There's a dot there. I'm going to show you the dot there too. Times 7 times, what's the square root of x to the 4th? I'll just reduce it, cut it in half by 2. So really quick, this is why they're showing you the rational exponents. So x to the 4th is x to the 4 halves, right? The square root of x to the 4th. And if I take the square root of that, and then if I just simplify that, that becomes x to the half. So turning it into the rational exponent helps you to see how we are simplifying the exponents under the radical, right? Okay, so then to simplify, I've got 2 times square root of 49 is 7, times the square root of 3, I can't do anything with, times x squared times the square root of x. So now everything that's not under the radical, I'm going to multiply. 2 times 7 is 14, x squared, and then everything under the radical can be combined. So 3 times x is 3x. There's part A. Okay, let's do part B. I'm going to rewrite it all under one radical first. So 2 times the square root of 12 times x to the 9 times 18 times x to the 5th. So now I'm going to be looking for factors that are perfect squares underneath the radical. 2 times 12 can be broken up into 4 times 3. I like that because 4 is a perfect square. I'm going to save the x's for now. 18 can be 9 times 2. I like that because 9 is a perfect square. And what I'm actually going to do is I'm going to combine these x's because look, if I add the exponents, I get a total of x to the 14. That's an even exponent. So if I take x to the 14, the square root of x to the 14, and I write it as a rational exponent, remember, the root is the denominator, and the exponent underneath the radical becomes the numerator. What is 14 divided by 2? 7. So now this becomes x to the 7. So I want that because that is a perfect square exponent that I can simplify. So now if I split the radical, I'm just going to draw that they each have their own little radical, right? I can simplify. So this becomes 2 times what's the square root of 4? 2. And what's the square root of 9? 3. What's the square root of x to the 14? X to the 7. What's left underneath the radical? I've got the square root of 3 and the square root of 2 underneath. That's left over. So let's combine everything under here. 2 times 2 times 3 is 12, x to the 7. And then I can combine my factors underneath the radical. 3 times 2 is 6. So there's part B. So again, looking for perfect squares underneath the radical because you can simplify those out. That's if it's a square root. You'll do a similar thing for cube roots, but then you're looking for perfect cubes. Example 3, an application problem. A light fixture in an ice cream shop is in the shape of an ice cream cone, and the cone has a height that is 7 times the radius. Okay, so the height is 7 times the radius. If we say r equals the radius, then I can write height as 7r. That's going to come in handy. The expression for the slant height, this diagonal height right here, is right here. Okay, the square root of r squared plus h squared, where r is the radius and h is the height. The slant height should be no longer than 24 inches to fit on the wall. What is the slant height on the cone with this radius? So we have a radius of 3. So first what we want to do is we want to turn this slant height expression and have it only have one variable. So we want to replace the h with our expression using the radius. Okay, so instead of h squared, we're going to put in 7r for h. That's what they did here. And then we're just square everything inside. So 7 squared is 49, and then we have r squared. Since we are adding like bases, or they're like terms, right? R squared. So we have 1r squared plus 49r squared. That means we have 50r squareds. And then we can simplify. So let's simplify 50. 50 is the same as 25 times 2, or 5 times 5 times 2. It might be easier to see like this. Okay, and then if we split the radical, we get the square root of 25 times the square root of 2 times the square root of r squared. Well, that's equal to 5 times r times the square root of 2. So this is the expression for the slant height. I'm going to call it S. Now, if the radius is 3, can we actually calculate it? Yes, so now we're just going to substitute 3 for r. So the slant height is going to be 5 times the radius is 3 times the square root of 2. And that is going to be approximately 21.2 inches. Can it fit on the wall? It says it's no longer than 24 inches. Yes, it will fit because it is less than 24 inches. Try it number 3. Another cone has a slant height S that is 5 times the radius. Okay, so I have an equation right here, or equivalency. So slant height S equals 5 times the R, or 5R. I also know from the previous example that the slant height was represented by this equation, or this expression, r squared plus h squared. That's probably going to come into play. I'm looking for the expression in terms of the radius, so I want to have just the variable r. So since these are all equivalent, I can ignore the s right now, and I'm going to just work with 5r equals the square root of r squared plus h squared. So the first thing I can do, I want to get rid of the radical. What's the opposite of taking the square root? Is squaring. That's the opposite operation, so I'm going to square both sides. When I do that, I get 25r squared equals r squared plus h squared. Let's get all the r squareds on one side. So subtract r squared from each side. What do I get? 25r squared minus 1r squared is 24r squared equals h squared. I want to get it in terms of h all by itself. So we can take the square root of both sides now. And the height is going to be the square root of 24r squared. Can we simplify that radical? You bet we can. So 24, that equals the square root of 4 times 6 times r squared. Split the radical. We can simplify that. I'm going to come up here. So then h is going to equal 2r times the square root of 6, right? Because remember, r squared, if I take the square root of a square, it just cancels out. So now I have the height in terms of radius. That's what I want. I wanted the height represented in terms of radius, and we did that just by simplifying. Example 4, multiplying and dividing radicals. So the product property of cube roots. If they are products, just like with square roots, you can multiply everything under the radical and put it under all one cube root. So that's what we're doing. Okay, so we have the same root, so we can put it under one big cube root. That's it. And then we're going to look for perfect cubes. So we're going to multiply 45 times negative 75, all under one cube root. And then we're looking for perfect cubes. So let's break down our factors first. So 45 we can break into 9 times 5, or 3 times 3 times 5. We're just breaking it down into its prime factors. Factor out the negative 1. And 75 is 3 times 25, right? Which is 3 times 5 times 5. Stay with me. I know I was thinking of perfect squares because 9 is a perfect square and 25 is a perfect square. But look, now I have 3 3s. I have a perfect cube. And I have 5 5s. I have 125. That's a perfect cube. So it can sometimes work out if you break it into the prime factors. Negative 1, is that also a perfect cube? Yes, I can do that. So now I have all perfect cubes, okay, which is what I want. So the cube root of negative 1 is negative 1. The cube root of 27 is 3. The cube root of 125 is 5. And then if I multiply them all together, I get -15. Letter B, divide. So we have the same roots, so we can combine them all into one giant square root, cube root. So I think how they're showing you is a little bit tricky. I'm going to show you a different way. That might make a little bit more sense. So since they are both cube roots, I can write them under one giant cube root, 15 over 405. Okay, now look at the base, what's inside my radicand. That is a fraction I can simplify. 405 is divisible by 15, so this becomes the cube root of 1 over 27. Now I'm going to go back and I'm going to split the radical now. So then each piece gets its own cube root. Cube root of 1 over the cube root of 27. Can you do this math? Yes. What's the cube root of 1? 1. What's the cube root of 27? 3. So I think this is a lot easier way to do it. So remember, you can combine things, quotients and products under one radical, and then you can also separate them. So each piece has its own radical, and sometimes that's helpful. Try it number 4. We're going to multiply or divide. Okay, so for part A, they both have cube roots, so we can multiply and put it all under one radical. I'm going to have 21 times 147. Okay, well, what is that? That equals the cube root of 3087. So now we got to think, are there perfect cubes in there? So what I would do is I would just take 3087 and see if you can divide it by a perfect cube, like 4 cubed, 5 cubed, 6 cubed, right? And as you go through and do that, you will see that 3087 is divisible by 7 cubed. So it is 9 times 7 cubed. So you can just take your number and start dividing it by 3 cubed, 4 cubed, 5 cubed, 6, until you get an even factor. Okay, so now I can do the cube root of a cube. So the cube root of 7 cubed is just going to be 7 times the cube root of 9. So that's it. The tricky part is just using your calculator to find a perfect cube factor in there. Okay, part B, same thing. I can put it under one cube root. And I have 225 over 75. Can you simplify that fraction? Well, what's 225 divided by 75? 225 divided by 75 becomes 3. So it's just the cube root of 3. That's pretty simple. So sometimes it's good to put it under one radicand and see if you can simplify the fraction first before you do anything else. Example 5, how can we write the quotient in its simplest form? Okay, we're going to get complicated. So again, we can write everything that has the same root under one radical. So that's what we did here. We just put it under one radical. And then we're breaking it into their factors. Okay, so 72 is the same as 8 times 9. That's what they did. I'll write it here. Okay, so 72 is the same as the square root of 8 times 9. And then I know 8 is a perfect cube. 8 is 2 cubed. Okay, 3,888. That is the same as, I'll try to show you here. It's 8, so there's another perfect cube. 8 times 486. Okay, so those are some factors. And then you can break up 486 into 27 times 18. So I have 8, which is a perfect cube, and 27, which is a perfect cube. So then if I take, I'm going to just write this over here. The cube root of 8 times the cube root of 9 over the cube root of 8 times the cube root of 27 times the cube root of 18. Okay, so each factor can get its own radical also. And now I can simplify. So what's the cube root of 8? 2 times the cube root of 9. Can't do anything with that. And then in the denominator, I'm going to have a 2 times a 3 times the cube root of 18. So the 2's will cancel. Don't forget, I have this 2 over here, the 2 at the beginning. I need that. Okay, so I have 1, 2 at the top. 2 times the cube root of 9. And then there's a 3 in the denominator times the cube root of 18. There you go. So don't forget, I almost forgot that 2 out in front at the very beginning. No, that's not very good, is it? So then, if I put my cube roots under one radical, so I'm going to have 2 over 3 times the cube root of 1/2, right? Two times the cube root of 1 over 3 times the cube root of 2. Well, the cube root of 1 is just 1, so this would be 2 over So if we get 2 over the cube root, 3 times the cube root of 2, then what they're doing over here is we don't like to have radicals in the denominator. So we need to multiply the numerator and the denominator by the cube root, which is the product of the cube roots in the denominator. We basically need to multiply by 1 so that we can get rid of the cube root in the denominator. That's what we're trying to do. So it's kind of complicated. So if we multiply by the cube root of 2 in the numerator and the denominator, cube root of 2 times the cube root of 2 times the cube root of 2 is just going to be 2. Okay, and then at the top we would have the cube root of 4 because 2 times 2 equals 4. Okay, so can you see what they did there? So we're just trying to eliminate the cube root on the denominator by multiplying over and over again by something equal to 1 to cancel it out. So then our final answer would be the cube root of 4 over 3. That is a much simpler expression. Try it number 5. Write this square root. It's a square root, thank goodness. It's easier to look for perfect squares in its simplet form. So let's first write each radicand in its factors. So I'm going to have the square root of 9 times 7. I know I'm going to use 9 because it's a perfect square. Over 98 is the square root of 49 times 2. Okay, 49 times 2 is 98, and 49 is a perfect square. So then I'm going to split the radicals. I'm going to have the square root of 9 times the square root of 7 over the square root of 49 times the square root of 2. Then I can simplify. Square root of 9 is 3. I can't do anything with square root of 7. Square root of 49 is 7. I can't do anything with square root of 2. Okay, now we got to get rid of the square root of 2 in the denominator. So that means if I multiply by something equal to 1 to cancel it out, right? So square root of 2 times square root of 2 is just going to give me 2, right? If I square a square root, it cancels it out. So that's what I want to do. I'm going to have 3 times the square root of 7 times the square root of 2 on the top over 7 times 2. That's what I want. I want to get rid of the radical in the denominator. Now let's simplify. Combine your radicals. You can use the product property of radicals. And so square root of 7 times the square root of 2 is going to be the square root of 14. 7 times 2 is 14. We made it to the concept summary. Good work today. Okay, you might want to review a couple of these to practice simplifying your radicals. Remember, you're looking for perfect squares that you can factor out. If you have any questions, put them in the comments, and make sure to like and subscribe and come back for lesson 3.